Time series is a revolutionary way to store data. It's less about individual values, but rather values over time, looking for rates of change and other emerging patterns in your data. An example is CPU statistics. When are they trending outside the norm so you can determine why performance lags are happening? RavenDB gives you querying capabilities which match the way you would keep time series data. You also have notifications to alert you when the state of your system has changed. You can plug time series values into machine learning models to track anomalies inside your data. Today, RavenDB CEO Oren Eini gives you a live example of time series data and machine learning solutions, demonstrating how you can monitor millions of independent data points to decipher the valuable messages your data is telling you. You will see how RavenDB compresses your data points, storing it in a very small amount of space. How to utilize a distributed database cluster to collect data across thousands of sensors and then replicate them to each node to consolidate inside your nearest availability zone. How to save even more memory with rollups that reduce your raw data into single data points representing time intervals like minutes or days rather than each raw point. Feel free to ask questions by clicking the Q&A button at the bottom of your screen, and Oren will be happy to answer them throughout the session. Enjoy your presentation, and here's Oren.
Hi, everyone. Thank you for showing for this webinar. This is interesting because I spoke about time series in the past. I spoke about machine learning in the past. Right now, I want to put them together, and it's not so much about the actual features as what you can do with everything put together. Now, I'm going to assume that you haven't seen all of the dozens of webinars we have done so far. So let's start from scratch. The first thing that we need to understand is what are time series? And they're pretty simple. It's a value over time. Right now, my heart rate is, if I can figure out how this is, my heart rate is 75 beats per minute. I'm very excited to talk to you. Now, this doesn't actually tell us much. This is data in a particular point of time. If my heart rate right now is 75 because I'm excited, then okay. If my heart rate is always 75, probably I need to do some exercise. So the point here is that a single value isn't meaningful, but the long stream of values is much more important. There are actually quite a lot of scenarios like that. Monitoring CPU, memory, disutilization, network, all of the sort of things is incredibly common to want to see the values, again, not as a single point, but overall. If I'm looking at my system, and right now I'm seeing that there is 6% CPU, tells me nothing, but because maybe I just hit a lolling requests. But if I see that over time my CPU utilization is at 6%, probably I can downgrade my systems and save some money. Same thing the other way around. If I'm keep running at 80% utilization, that's a problem. If I hit spikes every now and then, big request, I don't know, Monday 9 a.m. load, those sort of things, and I'm hitting 80% utilization, probably not something to worry too much about. Same things around thermometers, medical equipment, those sort of things. Time series data is all around us. This is typically boring data. This is data that is being generated by machines. It only makes sense to operate in large quantities. And that's important. That's important because when RavenDB, you typically work with data that is generated by, in the end, a person. I click on a button, I order something. There was some user action that created the data. I posted a new comment on my blog, those sort of things. With time series, the situation is very different. It's almost always automated processes, almost always they are, you're going to have to keep the data over a long period of time for it to make sense. And that means that we have to treat it differently. And RavenDB has a dedicated storage mode for time series. So let's see how this works. And this is simple. We have a time series, which is a point in time using UTC, and a set of values. And they're double. And that's about it. That's about as complex as it gets. Now, let's look here. And I'm going to create a new database. And I'm going to create a sample data. And we're going to look at some interesting details. So right now, here is the company information. Here is time series data, stock prices over time. You can see that this represents about 6 months or so of data. And now you can see here is the timestamp that I was talking about, and here are the values. And remember, we have 1 to 32 values. That's about it. Another thing that we have, which is important, is this thing. Every in the terminology, by the way, you have a time series, and the time series is composed of timestamp. Each row here is a timestamp, which can have multiple values, and then it gets tagged. Now, the whole idea with this format is that there are sometimes additional information that you want to record about a particular timestamp. For example, if I'm using a heart rate monitoring, it's important to understand what type of sensor capture that measurement. There may be different confidence values associated with each sensors. Oh, this is non-medical grade sensor. We can counter that. This is a medical grade sensor. We can counter that for so and so. So, and you want to track those down as well. So RavenDB allows you to tag a particular timestamp. And the idea here is that anything that you want to tell me about this timestamp, you're going to record that in a document and store the document ID itself as the tag of the entry, the timestamp that is involved. Why is that? Because for the most part, those details are the same. It makes very little sense to repeat those values time after each and every time. So we allow you to just store the reference to that, and RavenDB can optimize the fact that this one repeats quite often. Now, this is actually really important, because one of the factors that we have with regards to timestamps, to time series, is that in the end, you're going to have a lot of them. And we will get to that in a minute. Something that is really important to understand about the way that RavenDB manages timestamp. Timestamp are always about a particular document. So in this case, what you see here is the stock price for a particular company. And I can go to another company and see different stock price. Yeah, so not different stock, but different numbers for the stock. And this is important. This is important because it matters in how you model the data. Because let's think about how do I model the data of a let's say monitoring servers. So what data do I have? Monitoring. I have CPU, memory, this network. So these 4 numbers. And I would model that so I have something like this. So a document for each server, which contain details such as the CPU brand, number of cores, memory, disk, whatever. And then it is going to have a metric time series, which contain these 4 values over time, obviously. Now, each one of those servers is going to have its own different metrics, its own different time series dedicated for that. There are two primary reasons for that. One, in terms of modeling, it keeps everything consistent. The unit of work, the unit of operation inside of RavenDB is a document. And this is how you typically operate. Another thing is that it also allows RavenDB to optimize things very heavily because the data tend to be quite similar over time. It also means that if you want to do queries, your always queries on time series data, and we can see it here. Here is the stock price of this, and you can see this is how, here is the max stock price. Sorry. There we go. Here is the graphical format of the max stock price over time. And on a monthly basis. Now, every time, you can see it here, this is applicable for this particular document. This is important. Now, there are ways to do cross-document time series operation. This is when you're using indexes to do that. Not touching this breakdown. But again, those are the basic building blocks of time series work inside of RavenDB. Now, let's talk about what it means in terms of how is it actually sitting in storage. So it turns out that there is quite a lot of details around this. So remember that in our case, right now we saw time series sections, time series that we have very few values. So 100 values here. I think we also have something in employees, and again, 120 values. Not really interesting. This is small and minor. But we have to be prepared to deal with data that runs into the millions of data points. In a few months ago, I did a webinar on time series directly, and there I showed how we deal with over 1 billion data points in order to run interesting queries. Now, here's an interesting details. Time series are stored in segments. A segment is some section of the values over time, and it's limited both in size and the time that it carries. And we have multiple layers of compression on that. So we first use Gorilla compression, which is a compression format from Facebook dedicated for time series. And on top of that, we apply LZ4, and we can compress things quite heavily. So to the point of this is quite nice because you can squeeze a lot of data into this, and it means that when you run queries, you actually don't need to operate over the entire data set. You don't have to do an 11 million entries. This is because of the way RavenDB works. When we build a segment, we also compute the aggregation on that. So things like, okay, in this segment, I have this is the maximum value, this is the count of value, this is the total numbers that I have, stuff like that. When I'm going to go and execute something like this, which is an aggregation query, in this case, I have just 120 items. This is nothing. But if I had more values, then what would happen is that instead of aggregating over the individual values, I would be able to aggregate over the time segments themselves. In effect, reducing the n that I'm operating on by typically an order of magnitude or two. Now, so far I was I'm talking to you only about the sample data set. This is because you can go and play with that. Let's see some real world data. In this case, I'm going to show you a single document. This is me. And now this is interesting because here you can see this represents about 5 years of data. And that is actually the data for Fitbit, for this Fitbit and its predecessor. And you can see that there are quite a lot of data here. And you know what? Let's see what is the average heart rate over this time. Notice that it takes me 5 milliseconds to query over 5 years and 11 million records, close to 12 million records. Now, in this case, I'm doing that on a monthly basis. That's not really that interesting. Let's do that on a week basis. And again, things are fast. By the way, you can see here, I didn't, this is miss data. So you can see that, okay, he didn't wear the watch at that time form. Same things here, and I think in here as well. But for the most part, you can see that apparently I'm trending in this range. You can do all sorts of interesting observations on this data. Give me the sum, give me the count, a bunch of other things that would probably make sense. Time series also have quite a few features. You can, in this case, there are missing values. You can speculate. You can, there is a term for that, not speculate. You can fill the missing values with a bunch of strategies, and you can do all sorts of interesting things. But again, those are just queries over data. This is not what we're here today. We're here today to talk about machine learning and time series. It turns out that time series is very well suited to machine learning, mostly because this is all about numbers. Now, let's talk about what this means and how does it work. What can I do with machine learning on time series data? And probably the simplest thing that I could do is to say, hey, you know what? I want you to find outliers. You can see here, and let's do okay. So now what I'm saying, give me, okay. So this is my average heart rate over 2019. 2020, no one did anything. Now, if I would ask you, find me the outliers, find me the things that are different, it would be very easy for you to say, hey, this is different. This section is significantly different from everything else. If I focus on this guy, apparently there are spikes here. Don't know what this is about. And again, spikes here that are interesting. But if you tried to ask these questions from a computer, that's much more complex. This is why there are mathematical formulas, which I would absolutely and frankly admit I have no idea. This part is magic. But independent and identically distributed values, which allows you to do all sorts of interesting details. Now, again, I have no idea how this works, so I went into Google and asked it, how do I find interesting things? It pointed me to ml.net. Hey, that's viable. I can actually make use of that in RavenDB. So let's see how I can find outliers in my data. In order to do that, I have this guy. And this is an index. It's an index that is going to be operating over time series data. And this is a time series segment, and we are going to be processing that. and then we'll just output the when that outlier happened, what is its value. You can see all sorts of interesting details here. Now, here's some interesting stuff. First of all, you can see that I'm using RavenDB's ability to pull additional assemblies. In this case, I said, oh, I want these 3 assemblies from NuGet. So I can get ML.NET machine learning integration directly inside of RavenDB. And then I wrote this code. There's a whole bunch of stuff here, most of which isn't that interesting, but this is the thing that is most interesting for us. We are going to get a time series segment. This one has a list of entries and the value for that entry. We're using ID spike. ID is independent and identically distributed spike. And we're going for confidence of 99%. And we're building here the list of inputs, transforming them into this, and then we're saying, okay, give me the predictions. This is, again, I'm explicitly not touching how mm.NET working. I made sure to use examples that are one-to-one from what you can find in the ML.NET examples, so you can go and read more about them there. Presumably, if you're interested in machine learning, you might know more about them than I do. But the whole idea is that in here, I'm detecting an outlier and throwing it out. So now I have the at and the value, and now I can query on top of that. Now, interesting enough, let's see. Okay, so you can see interesting data. Presumably, by the way, look at the numbers. For some reason, I was up and doing something very late at night, and apparently I went up some stairs at this point. No idea what's going on. But notice what's going on. This is using a couple of features at the same time. First, we're using NuGet integration in the indexes. We are pulling the time series data. We use the ability to have additional sources to integrate that, to actually take data directly from RavenDB, take the segment, pass that to ML.NET, and process that. Then we output the data, this guy, and now we are here. And now we can decide how to project it out. Now, this isn't just give me the data. This is throw the data into an index so I can query on that. For that matter, let's see if I can try to do something. Here we go. Notice what's going on here. I'm now running a faceted query over the result of a machine learning operation. The amount of flexibility that I have here is enormous because I don't really have to think about stuff. I can reuse a lot of existing infrastructure and knowledge. And then I can just expose that to the normal RavenDB operations. Now, this is it in terms of outliers. Admittedly, this is not really that interesting of an example, but consider what happens if I'm looking at this from the point of view, oh, I want to see spikes in a number of errors, or did at some point the network traffic on my system hit a big jump or big drop. A big jump may mean that someone is crawling to my website. A big drop may mean that I don't know, Fastly has been down right now, so a lot of websites couldn't get in. Even if my entire system is okay and all metrics are in green, looking at, hey, there is a problem here, just based on that information, can be quite interesting. What is even more interesting is that all of these values are not computed on demand. This is an index, this is happening in the background, and then it just sits there, which allows me to apply additional analysis on the data afterward. Think about what it means and how I can do all of those sort of interesting things around. Now, the next thing that I want to look at is something called a change point. And Outlier is find me a value that is outside of the expected norm. Change point is when the expected norm itself changes. For example, if I go on a run, my heart rate is going to change and stay changed for a while. Now, luckily for us, this is something that ML.NET knows how to do quite easily. So again, I'm using ML.NET. And now I'm going to look at compute change point. Notice that in here, I'm also adding this explain. This will be relevant in a minute. So now, detect IID change point, independent and identical distribution. And here they get the income result for these segments, transform that, and get me the predictions. Now, this is where it gets interesting. This is a change. We check if the heart rate that we have here is increasing or decreasing, and output this out. And again, return that to the user, and now we're done. And now at this point, you can see value, and here are the changes that you see. Now, let's see how that works. I can see that this is an interesting detail. From users, where ID. So what I'm doing right now, I'm asking it, give me the raw values for the time frame. There was a change point there. I want to see that. And the change point that I have was at 10 something. So probably detected that, hey, I was doing something and then it dropped and it detected a change point here. And probably around, let's say, dear God. So here is a messed up situation. You can see that these values here are in local time. This value here is in UTC. So this is 2 hours difference. So you can see that apparently there were about 3 minutes or so of big activity. If I'm going to go here and look at the value, and it was okay. That's interesting. Should have been 1 second. I wonder what's if I messed up the time zone. No, this is it. Okay, now I'm confused. Order by at. Okay, that's cool. Apparently I have no values at that time. Oh, I do, but they are later. I think I messed something up in the query here because it certainly looked like it should have worked. Okay, I'm not going to look into this in more detail because I don't want to waste your time. Let's make it easier for me to operate. What you can see here, let me just take all of this data. Okay, so now I'm going to go here. Well, if I have a previous value, let's put it there. Try it like this. Here we go. Now I have val and I have previous. Here we go. So what I'm doing right now, I'm updating this document, this index, which is going to force me to reindex all of the data. Now doing that intentionally to give you some idea about how fast this is going. As a reminder, this is the number of docs that are indexed, but this is actually wrong because we're not indexing documents here. What are we indexing? We're indexing the time series segment, those 2 kilobyte operations that are compressed using multiple levels. So at this point, it's almost done processing 12 million entries. And this is great. So let's see where I can find something. Well, value equal, let's say, 120 and previous. Nothing. Okay. This is interesting. Okay. So now I want to see these details. So let's go and look at the query. And so this is here, certainly look like a change point to me. You can see, we can zoom in actually. So here you can see this is roughly 45 and 11. There we go. This is checkpoint. This is the top of the line. And now here we're going down, etc. Now, this is actually quite interesting. Now, this is admittedly relatively simple model. I mean, no, it's not even a model. It's just doing relatively simple processing on the data. This is mostly because whenever I look at machine learning topics, they get crazy fast and then they pull up the math. And then I have to pull pen and paper and try to work things out, and it takes too much time. I don't want to go into the minutiae of how machine learning works. I want to give you details of how to apply that inside the context of RavenDB. Now, so let's look at that. So we know how to find outliers. We know how to find change points. This is not done yet in our terms. We still have quite a lot of things that we can do in terms of machine learning. So one of the interesting details can be seasonality. What do you mean by that? Let's assume that I'm monitoring CPU metrics of my servers. And I know that every Monday morning, 9 a.m., there is a big spike. And every 5 p.m. on each weekday, then there is a smaller spike. I can train a model based on that information and then apply that during the indexing time. I have a whole webinar discussing how you can do that. So you can watch that. This is the link. And I will actually post that in the chat as well. So you have access to that. And here we go. So now, then for that reason, I'm not going to talk about how to actually use a model, but I want to talk about the scenarios around that. So the first thing that we have to understand is who trains the model and what sort of training is necessary here. One of the first things that we have to ask is, are we training a model on a per user basis or per server basis, stuff like that? It's possible that you says, oh, you know what, I want to, let's go with the server scenario. Each one of my server has a type. So those are the web servers, those are the cache servers, those are the DB servers, etc. I'm going to train a model for each one of them independently. And then I'm going to apply that model during indexing on the data. Now, something really important about this, when we talk about applying the model and running this for indexing, this isn't meant to be something that you necessarily going to alert yourself on. I wouldn't expect you to use RavenDB and ML integration in order to send an SMS, hey, the servers are broken. Instead, you would typically apply that in order to generate information. Oh, you're going to go to the website and says, hey, here are some details that we figure out about your scenario. Or maybe you would use that in order to drive deeper into the pipeline. So in the context of servers, I would typically do a model per type of server. In the context of users, I may want to group them by their features. So if I have heart rates, so male, female, age, are they active or non-active, those sort of things. After I train this model, then I can start applying that to each one of them independently or globally. I might want to say, oh, all of the males 35 to 45s are going to get this model, or I might want to train them independently based on historical data. That also leads to an interesting observation about what happened when I'm updating my model. How am I going to handle that? And there are two typical ways you would do that, you would manage that. The first way is to say something like, hey, I'm going to, every time that I update the model, I'm going to re-index all of the data, recompute all of my prediction about what's going on. The other side is to say, you know what, no, there is no need to do that. We're going to keep the existing data, just compute all new data based on the new model. And that's something that you can select to do when you build the index inside of RavenDB, because that depends on how you define where do we fetch the model from and how do we handle that. Now, another really fun thing that you can do with this sort of system is you start being able to ask questions across across users or across entities and time series. Or show me, let's say that we are tracking CPU statistics. Okay, show me show me the servers that are out of capacity, that are might be reaching critical point. Another thing that you can do future predictions. So based on the information so far, when are we going to actually hit a failure mode? So lots of stuff like that you can now make it easy to consume the results of machine learning processes. And it's important to understand that in almost all cases, we're talking about using RavenDB to run the predictions, not to run the training. That is a completely separate topic. Now, I think that we got some really good questions ahead of time. If you have questions, feel free to use the Q&A button right now, but I will answer those and then come back to the questions, to the live questions right now. And first one is from Muhammad Abdullah. NetCDF and Grip2 format useful in time series? Probably. I have no idea. It doesn't matter. When you work with RavenDB, you're pushing the data into RavenDB itself. Once you do that, then that information is going to be stored inside of a RavenDB, and then you can apply on that. You can process that using this sort of code, where you operate on the segment, you model the data as you need, and run it from there. Zulkarnain Anwar, I hope that I'm pronouncing that properly. How can we improve our work with some automation? Mostly included this question because the cheeky answer is use RavenDB. It's going to automate a lot of stuff for you. Now, more seriously, when we talk about automation, what are we talking about? Generating new indexes, automating the process of configuring values out of RavenDB, already there. You don't need to manage schemas. You don't need to manage a lot of stuff with RavenDB because it's going there. Zulkarnain, if you have more specific details to this question, I would be very happy to discuss this further. But in general, you can automate everything inside of RavenDB. This is quite easy. The only question is, what do you want to do? David Parent wants to know, learn temporality of RavenDB and how they differ from traditional RDBS systems. Well, traditional RDBS systems don't offer time series. There is timescale.db, which I think is based on Postgres, but others, they just give you a table of date and value and take it from there. And the problem is that this is actually not that efficient. Let's do some math around that. And let's go here and discuss why this matters. Let's say that I have date and value. Date is 8 bytes, value is 8 bytes, which means that each entry is 16 bytes. There might be also some tags here, but something like that. So 16 bytes times 256 values tells to 4 kilobytes. Notice that RavenDB can fit that in less than kilobytes, so that's 1/4 of the storage. It also means that queries on time series have to go over all of those details, whereas Raven is able to run those over the segments themselves, which already did a lot of operations. Now, this is actually something that I forgot to mention. You can see that I have 2 time series here. One is the heart rate and the other one is heart rate daily. And this is similar to how RavenDB actually manages segments internally. You can see that in the original time series, I had just the heart rate, the bit per minute. In here, I have the first and last heart rate of the day, because this is a daily time series, the minimum and maximum value, and then sum and count. Now, if I wanted to ask a question over this period of time, notice that this represents about 100,000 items. So going over distant records, what is the maximum amount that I had? And I can tell you that this is this one, without going over 100,000 items, because this is already pre-computed. This is already done on a segment basis. Now, this isn't actually how RavenDB works, because segments don't necessarily map to a particular time frame. This one was generated by time series policies. And you can see that RavenDB actually allows you to manage time series in quite interesting ways. We're going to say, okay, for heart rates, we have the notion of keeping the data forever, but aggregating that on a daily basis. I can also say, you know what? After 6 months, delete the data. Sorry, not this one. Cancel. Discard, sorry. Let's do this again. Here we go. That's the iteration that was it. So now I'm going to say, okay, the raw data should be done on a 6 month basis. And then we are going to keep the daily data forever. And this works like that. So all of those means that working with time series data is quite different. It gives you a lot more power, flexibility. You don't have to manage everything on your own.